So for the same data set, the model, and back to Jonathan asked that question. If we use the Kronecker product of two unstructured in the repeat statement, then that means we can ignore the random intercept and the interslope over there, right?
Yeah, I think you're like we're talking about. I think you're going to saturate your model. Um, it may depend though. Like you might have some other random effects, maybe defined for another experimental unit, like hospital or a scanner or something other than subject that may still be helpful. But in terms of the repeated measures for a subject, I think once you saturate the structure for a subject, and you probably do that if you do the unstructured by unstructured, then in most cases, I won't say necessarily always, you know, but in most cases, I would think that you would not need random effects for subjects. Now, if in your inference, it's important for you to do inference for subjects, then you might take a different modeling approach. You might add random effects and then not, you know, use as complicated of an R structure. So some of the decisions may depend on the inference you're trying to make. But if it's clear, if it's just simply in modeling the repeated measures, then I would say, yeah, you probably have saturated it with the unstructured by unstructured.
Thank you.
Sure. Other questions you guys have before we walk through the quiz? So I graded these yesterday, and I felt pretty good. I felt like people, pretty. It seemed like good preparation, and it seemed like the contrasts and the estimate statements. I think people did pretty well on those. Specifying the models generally was pretty good. The one the one point of confusion I think that people had was, the way I teach this course, there's three models of interest. There's the observation level, there's the subject level, and then there's the complete data level. And so for number one, part B, it seemed like a lot of people were giving me the complete data model rather than the subject level model. And that really, to get to the complete data model, you have to go through the subject level model. So, I didn't take much off for that, but really, there's three levels that we can write the model at. 1A seemed pretty good. Really, it seemed like most people got this one. Writing the observation level model, and in this case, we have a class variable which is group, and then time we're going to model as continuous. And I mentioned above that we already established that we don't need more than the linear term. So you just add a slope. But importantly, you need to have x in there. So a variable, so in this case, x is time. Actually, let me open up so I can write on top of this. I'm going to open up the Word version. It's a little bit easier for me to write. So just so so x is equal to time in this model, and you might have other covariates too, but I wanted to keep it simple here. But you definitely need the predictor itself and its coefficient, and not just one element, right? Because the coefficient is going to be the slope for that predictor, so that's important. But otherwise, it seemed like people got this one. As far as indicators, we have, in this case, I use H for group, J for time, I for subject. And so if we have X sub J, that's going to be the actual time, whereas the indicator J is going to be the first measurement, second, and so forth. So that would, J would go 1, 2, 3, 4, but the actual times XJ would be associated with those would be 1, 2, 3, and 6. But the biggest thing is that we have, you know, whatever indicators you introduce on the left, you should see on the right somewhere, and vice versa. I wrote a less than full rank model, and I think most people actually wrote less than full rank models here. For part B, this was what it would look like for a subject that occurs X sub I, what it would look like for a subject in group 1. And I thought about this as because I was actually writing the solutions out as you guys were taking the quiz, and I'm like, well, it actually, you know, XI is going to look different depending on if they're in group 1, group 2, or group 3. And if you wanted to, you could add a group indicator on that. So like for a subject that's in group 1, you could say X1I is this one, X2I would look like this, and so forth. If you wanted to, you could do that. Z, this is one where people sometimes added an extra column of 1, like 1 column of 1s for the whole thing. But if you have random, you know, random intercept for subjects, then we'll have the first column is going to relate to the first subject, and you only want 1s for their 4 repeated measures, and then 0s for the rest. And for the second subject, then we'd have 1s in the next 4 rows, and only those, and so forth. So this is what Z would look like. And the G matrix, the complete data G matrix, would be sigma B squared times the identity matrix. Okay, B would be, and this I'm just doing because a lot of people did it this way. I didn't ask for this, right? So this, you didn't have to write this, but I'm just sharing it to distinguish the complete data model from the subject level model. And in terms of the writing the mixed model, the subject level model is just look like this. Right, where these are vectors, so the Y sub I is going to contain, so this would be, the dimensions would be Ri by 1 and so forth, and there would be, on the right side, you have vectors or matrices as well. And so in general terms, these don't look too much different. The complete data model would look like this. In this case, you stack Y1, Y2, up to YN. You stack that to get your Y. And similarly, you either stack or place along the diagonal the elements on the right side. And if you go back to the slide set, it lays that out. So that's distinguishing the complete data model from the subject level model. Any questions through 1B?
I have a question, Matt.
Yeah.
So for the very first part of the question, if you remove the J subscript, how would that change the parameterization? Because when time is continuous, I don't see why you would want to have a subscript for time.
Yeah, I see your point. And like I made a mention here, it might seem a little redundant to do that, right?
Right. So if you do pull that out, though, how does that change? Or can you not pull that out?
My response is like, there's a little bit of artwork when you write statistical models, and there's some different ways you can write it. I think really what we're doing by adding the J subscript, it's more to indicate that there's repeated measures on subjects. And I'm doing it more for the left side than the right. But like I mentioned, if you add an index on the left, you really should show how it relates to the right side as well.
Right.
So really, I'm doing it for completeness. If you were to take off, the problem is if we took off J, just like on the X here, then it's hard to see how, where do those repeated measures come into play? By including it, it's easier to see that, oh yeah, the repeated measures are on time. And the downside is it seems a little bit redundant. I agree with that, but the upside I think is stronger in that you're accounting for all measures. And really, I think it would be okay, like if you were to say Yij, you're accounting for all measures, because as long as the subject index is unique across a study, then Yij is really all you need. The reason why I include H is because we need it on the right side. And since we have it on the right side, that's personally, I feel like it's good to, like I said, it's good if you're going to have it on one side, it's good to realize it on the other. But you could take the H off here if that wasn't a big deal to you. So the indicators, like, they're not changing the value. They're just little pieces of clothing, like to tell you what it's about, right? So if you took off the J, the model will be the same. It's more to understand what the model's about. And the problem is then, like, if you take off the J on the X variable, would you also take it out on the epsilon? If you did, then it would be, then you're not indicating that you have different errors for different repeated measures, right? So it's funny because there's always some pros and cons to different approaches. Like I spent a lot of time trying to write models, you know, and the best way to do it. And like I said, there's a little bit of art to it, but it's like, you want people to understand what the terms are associated with. And there's some technical things that are important that are correct or not correct. Like for example, if I put an I subscript on alpha, what would be the problem with that?
You could change groups. It would be
You don't need a
indicated.
group anymore.
Yeah.
It's
So-
just individual.
Yeah, Carrie, go ahead and finish what your thought.
It would indicate that people could change groups.
Yeah, and also that's true. And also, what were you saying, Randy?
So that means we just ignore the group and we see the subject as individual and it has effect.
Yeah, and the thing is, like, if you put an I indicator on, those are both good. If you put an I on the alpha, what you're saying is that every subject has their own parameter, right? And that's not, I mean, that's what you're indicating, is that if you're allowing that I on there, so if we have alpha, you know, 1H, alpha 2H, alpha 3H, and so forth, that's suggesting that every subject's going to have their own alpha parameter, and it could vary between subjects. And to me, that would be incorrect. So there's some technical things that, to me, seem like are going to be right or wrong. But then there's other things, and back to Jonathan's questions, that you might be able to do it one way or the other, and there may be pros and cons. To me, it seems a little redundant, but I think there's an advantage to keeping that J on the time.
Can you?
So J is going to be like the order number of observation that you're taking, whereas X is the actual value. And so I'm distinguishing, you know, with the measures that we have here, how those are different. Carrie?
Can you talk about why there's not an H on the epsilon?
You could add an H. You're right, and and that's another one that I struggle with. I think it could go either way. You could add an H onto there, but the thing is, like I mentioned, the I and the J are uniquely identifying an observation. And so that's why I think it's okay to not have H on there, but you're right. I'm like 50-50 on that one. I could, I think adding the H would be okay there, and it would be, is good. Similarly, you could talk about not having it on the Y, but like I said, I like to have everything on the left that you show on the left appear on the right. That's my thinking. So it's funny, like there's, it's a lot more complicated than it might seem, and there's different ways you can do it, but there's some things that technically need to be there as well. Like you could have added I within H on the random effect, because the subjects stay within groups, right? So you could have said BI and then within parentheses H, and that would be fine too. Any other questions on 1A and 1B?
I have another question for the Z sub I matrix. So how would you combine all these Z sub I's to get the full Z if you don't include all the other zeros that go across column wise?
Yeah, so the Z sub I is here, and then the full Z matrix is what I showed here.
Right.
Tell me what's your specific question then?
So how would you combine the individual Z sub I's to get that full Z? Because I feel like you would need to include the zeros that run across the columns. And that way you would stack your Z's, your Z sub I's, and then that would yield the Z.
Why don't I do this? I'm going to open up. That's not what I want. This shows you how you go from the subject level model to the complete data model. So you stack the Y's, you stack the X's, the Z's, the subject level, for subject 1, that's going to be in the first diagonal element. For subject 2, that's going to be in the second diagonal element, and so forth. And as long as you're assuming that subjects are independent of each other, the off-diagonal matrices are going to be 0. So that's how you go from the subject level to the complete data level for Z. Then you stack the random effects and you stack the errors.
But for the individual G, the ZI, it should be a matrix inside of it, right?
Yeah. So this is like Z1 is a matrix, right? And Z2 is a matrix, and this 0 is actually a matrix of zeros. And to indicate that, I've bolded them, and I indicated the size of those here as well.
Yeah, but in your solution, it's just like one column, 1.
Yeah, it happens to be Q is equal to 1 for that example, so it ends up being just one column. But that would be the Z matrix for subject 1, and it simplifies to a vector, essentially for that data. All right, so for C and D, like I said, I felt like people did this pretty well. And actually a lot of people did what I did in the solutions here, is like when you're comparing one group to another, I still do this because, like, off the top of my head, I forget, are the group effects going to stay in or fall out? Are the time effects going to stay in or fall out? And sometimes I forget how that works unless I actually do the difference. So really, you only had to turn in, this was the answer, right? But I did that by taking the difference at 5 months between group A and group B. And you can see that I'm actually using my mouse here. Okay, let's do this. So this would be group, and then this is time, right? And this is group by time. And so this would be like, if you write it generically, this is how it looks. If you do it in SAS, you don't have to include the intercept in time since there's 0 in that. So you only have to worry about the non-zero part. So you have group 1 minus 1 0, group by time 5 minus 5 0. There's 1 degree of freedom for that test. So we can do the estimate statement. We don't have to do the contrast. And we get an actual estimate of the amount, the mean difference between group A and group B at time 5. For R, so I know a lot of you use R, right? And, you know, Jonathan's been sharing some code, and that's actually helpful for me. I've been able to learn a few things, you know, using the M means, and that's relatively new in R, but that's a good way to get estimates. And then you can add on contrast to that. Is there something like estimate that's comparable to that?
You can do estimates in the EM means package, yes.
Like custom ones that you.
Yes, you can.
Okay, what's the argument they use in R for that?
So it's the same. So it's a contrast. So you use the contrast, but in this case, you would specify a 1 vector instead of a matrix.
And then when you specify the 1 vector, does it automatically give you the estimate and stuff?
Yeah, it does a t-test instead of the f-test.
Oh, okay. Okay, good. That's good to know. Keep learning. So for part D, to compare the slopes, you have 3 groups, right? But we have 2 degrees of freedom. So you only need to specify 2 rows. A lot of people, not a lot, some people wrote all 3. And I think the test actually still works. So I didn't take much off, but really you only need 2 of the 3 because there's 2 degrees of freedom, right? You can use 2 equations to express the test. And in this case, you need contrast in SAS. It won't work in estimate because you have multiple rows. You need to use a contrast and do an F-test. So this is group by time interaction, just another name. So it should come out with the default output, even if you don't ask for the specific test. 2 degrees of freedom for the test. We talked about a little bit in class about, you know, covariance structure. Like we do have one, you know, but it's a compound symmetric. By adding the random intercept, we have a compound symmetric structure for Y, which is much better than nothing. But we can probably improve on it by doing something that's more time sensitive. So the spatial power structure, I guess we did, you know, through the homework, we did talk about that, I guess. But if for some reason you know, you had the unstructured in mind, which we did talk about more up to this point, either one of those is fine. And then you could use AR1 with that trick about adding rows to the data. Any of those are reasonable responses, but I think I would try to handle the unequal spacing and not just assume that like the regular AR1 would work in this case. You know, occasionally you get funny results, like the AR1 actually has the lowest AIC, has lower AIC. It's like, how is that, you know? Like intuitively, it just makes sense that the continuous AR1 would be better because there's the same number of parameters and it's handling the spacing better. Any questions up through number 1? Number 2, say we perform a longitudinal study and fit a mixed model, you're going to perform custom tests. So in estimating fixed effects, we know SAS uses a G-inverse. It doesn't use a set to zero approach. It uses a G-inverse, but it seems like it's the same as a set to zero approach. R, honestly, I don't know if it uses a G-inverse or a set to zero. I'm thinking it actually uses a set to zero approach, because the reason why I think that is because it actually doesn't have a row for it in the estimates. I see Jonathan is agreeing. You think that's true too?
Yes, I know it's true because you can ask for the modeled matrix after you fit the model, and it'll return a matrix with less columns than you.
Okay. So yeah, I think, and so that makes sense based on what I'm seeing as well. I think it's a set to zero approach. Regardless though, what we've learned about estimability is that, you know, whether you think of it as a set to zero or G-inverses, we know that if we're talking about estimable functions of parameters, those things are unique and they don't depend on the approach, essentially. And that's why we would expect the test statistics to be the same. Okay. Now, if you're talking about specific beta estimates, and I probably should have added that in this question. I'll do that next year, but the specific beta estimates do depend on those things, right? The linear combination of those that are estimable don't depend on those. So we'd expect the test statistics to be the same. The degrees of freedom, those are just, you know, they're all over the place. Like R has their defaults, SAS has their defaults. If you were to say, you know, assuming that DDF is the same, then those wouldn't differ and the p-values wouldn't differ. That would be an acceptable response. But I think most people realize that R and SAS, they're just different and they have different defaults. And so the degrees of freedom, really the order I should have had DDF as number 2. And then consequently, if the degrees of freedom, denominator degrees of freedom are different, then in turn, the p-values will be different. And it may not be by a lot. These methods are typically going to give values that are pretty close, if not the same. And for large data sets, even if the methods are different and the DDF are different, the p-values shouldn't change too much, but they will depend on the denominator degrees of freedom. Any questions on that one? Then the last one was the PCA, and just, I think most people did this pretty well. The first principal component is a linear combination of the original variables that maximizes the variation in the data. And one easy way to see that was with the variable, the data set that had 2 variables, the pre and post values. And you can see that it went through the points and captured the most variability in doing that. The Ramus data was another example where the weights were actually pretty similar between the 4 time points. And so it was essentially saying that the average size is the most important feature in the data in terms of variability. It's capturing the most variability. But that's not always necessarily going to be what PC1 is. It's not necessarily a weighted average of the original variables. It's a linear combination, right? And what's the difference? Those are sometimes the same, but what's the difference between a linear combination and a weighted average?
The ones with time points that are more variable will hold more weight in your, I feel like it's less influential to like extreme outliers.
Okay. That's a good response. That wasn't what I was looking for, but that's a good response. Yeah. Anybody else?
Because in this case, we just ignore the outcome. We treat outcome as a variable in the PCA because it's unsupervised. Is that what you're asking?
I think maybe I need to just kind of be a little more specific in what I'm asking. Sometimes that happens. I ask something that's pretty general, and it could be interpreted in different ways. So let me be more specific in my question. So PC1 in general is going to be something that looks like this: a times y1 plus b times y2 plus c times y3 and so forth. So that's in general. For this to be a weighted average, what do you know about A, B, C, and so forth, those coefficients? They could be different, and that's why we say weighted, right? They don't have to be the same value, but what would you expect, like for an average? And again, this could depend on what you mean by, you know, how you define your terms. But to me, a weighted average, they would all be positive. For a weighted average, the weighted indicates it could be different. But for it to be an average, I would think that that those coefficients would be positive in my mind. So again, it kind of depends on how you define the terms. But that's how I would distinguish those. So I think saying it's a linear combination is a little more general. And if some of these are negative, then it's indicating something other than an average. It could be like a linear trend or something like that, right? So, and that feature could be stronger. The average doesn't have to be the strongest feature. The linear trend could be the strongest feature in the data. But that, you know, as an example, with the Ramus data, it was the average. That was the most important feature in terms of variation. Any other questions or, you know, on this or in general in the class, like right now, if you guys have any questions, or I'm just opening it up.
If that's the weighted average, should we have a constraint that the A, B, C or something just is actually in a probability simplex?
They could be like, so for PC1, those A, B, C, those are real numbers, right? And I don't know if those are constrained. Like, it's possible that they can't run off to infinity. But basically, I'm saying, you know, based on what I think of as a weighted average, to me, it makes sense to think of those as positive, or at least non-negative values. So they're coefficients, and they are not restricted to be like probability values, or, you know, between 0 and 1. They could be greater than 1. So does everybody here have an idea for the data project? Data for their project? Some still thinking? Okay, so like I would say, you know, within a couple weeks, probably you want to figure out what to do. Like the way I've taught the course in the past is like, I actually have a timeline, and I have things that were turned in, like by, let's say, mid-October, you have to figure out your data. And then a couple weeks later, you have to do some simple analyses, some graphs, and some descriptive statistics. And then a couple weeks later, you have to do some initial modeling. And I have these turn-in times. And I think I'll probably do the same thing, although I'm not sure I'm actually going to collect it, but I'll just have a timeline so you guys know, where you should be. The thing I don't want is to have you guys, wait and then pull an all-nighter and do the project the night before it's due, like my son would do. Both my sons actually. My daughter is the one who's really good. She plans ahead and stuff. And why is it that guys are, do that? I don't know. I think I was kind of the same way too. But I want you guys to work ahead, and not just because it's going to be, easier and you get more sleep the night before, but that will allow you to think about things over a longer period of time, and that usually leads to better work. And I also want you guys to be able to consult with me as you go along and get input from me about things that you might try. But I haven't figured out, it's harder this year because we're doing it remote. I typically, in the past, would meet with people individually and talk about it. But I might put that, I think that's still a good idea, but I might put that more, toss the ball in your court and just, you need to pursue me if you want to talk about specifics. I think that's probably how we're going to do it this year. So I would encourage you to do that, but I may not make it official. Any questions on the data project?
So the data that I have at work is like largely binary outcomes, and I know we're going to get to that eventually, but to be able to work ahead, is it in our best interest to really find a continuous outcome? It's a little harder to find, I feel like.
I would encourage you to do the binary outcome. And I know that you're right, there's kind of a downside because you're having to wait a little bit longer to see the methods that we apply to it. But I would say just work ahead in areas that you can, do some descriptive stuff on the binary data, stuff that you know already, and just start doing the pieces you can. And then the modeling, in a couple of weeks, we're going to start learning about generalized linear models and longitudinal logistic regression. But the reason why I like it is because I don't want everybody doing the same thing, like everybody doing a continuous outcome with 4 time points. It's nice to see different data. So I really want to see those, the binary outcomes, and it's going to lead to more unique projects and interesting presentations that subject, that you guys will be able to appreciate, just seeing the different types of data we can model in the class. So I'd encourage you to keep with the binary. And you can also look ahead a little bit if you want, review the slides ahead and talk to me if you want to kind of work ahead a little bit that way. Any other questions you guys have? All right, so thanks, and keep thinking about your projects, and just let me know if you have any questions. Otherwise, have a good rest of your week and weekend, and we'll see you Monday.
Thank you, you too.
Okay, see ya.